You're standing outside on a clear night. You look up. Somewhere up there, through the dark, is a star. You've seen it your whole life. Maybe you've even named it in your head, the way people do. That little pinprick of light has been there every winter, reliable as anything. You've watched it from your backyard, your bedroom window, through car glass on late drives home. Here's what nobody tells you when you're staring at it. That star is dead. It died, burned out, collapsed, exploded into the void, roughly 600 years ago. But the light from that explosion hasn't reached you yet. It's still travelling, still crossing the incomprehensible gulf between where that star used to be and where your eyes are standing right now. And when it finally arrives, when the shockwave of photons from that dying star finally washes over Earth, people will look up, see a brilliant new light in the sky, and think something miraculous just happened. They'll be wrong. It happened 6 centuries ago. They're just now finding out. This is the fundamental nauseating weirdness of living in a universe this large. Space is not just big. That word, big, doesn't even begin to do it justice. Space is so utterly, catastrophically enormous that even light, travelling at 299,792,458 metres per second, fast enough to circle the entire Earth 7.5 times in a single second, takes years, decades, centuries, millennia to get anywhere meaningful. The nearest star to our Sun, Proxima Centauri, is 4.24 light-years away. That means the light you'd see from it left 4.24 years ago. If Proxima Centauri winked out of existence this morning, you wouldn't know for over 4 years. The centre of our galaxy, the Milky Way, our home, is 26,000 light-years away. The Andromeda Galaxy, our nearest large galactic neighbour, sits 2.537 million light-years from where you're sitting right now. And the observable universe, the sphere of space we can even theoretically detect, stretches roughly 46 billion light-years in every direction. 46 billion light-years. Let's put that number in context. If you could somehow shrink the entire observable universe down so that Earth was the size of a single grain of sand, the observable universe would still be about 800 kilometers across. You could drive across it, if it were a road, in about 8 hours. But your grain of sand Earth would be invisible. Not small, not hard to see. Physically invisible. Smaller than an atom in that scale. This is the problem. This is the deep, existential, keeps physicists up at night problem at the heart of all space exploration. We are trapped. Not trapped by technology, though that too. Not trapped by politics or funding or international cooperation, though yes, those things too. We are trapped by physics itself, by the cold, uncaring geometry of the cosmos. Because even if we built the most perfect rocket imaginable tomorrow, a machine that ran on pure efficiency, that suffered no mechanical failure, that carried enough fuel to accelerate forever, it still couldn't break the speed of light. And without breaking the speed of light, getting anywhere interesting in the universe takes not years, not decades, but geological timescales. A trip to Proxima Centauri at the speed of our fastest spacecraft, the Parker Solar Probe, which moves at about 690,000 kilometers per hour, would take roughly 6,300 years. 6,300 years. The Roman Empire hadn't even started yet 6,000 years ago. Humans hadn't invented writing, and we'd still be in transit. So when people ask, why do we care about faster-than-light travel? This is why. Not because of science fiction, not because we watch too many movies, but because the universe is so vast that without it, we are essentially isolated forever on this one small rock, watching the rest of the cosmos from a distance, unable to reach out and touch any of it. The dream of faster-than-light travel is, at its core, the dream of not being alone. And here's the thing. Here's what makes this entire subject so electrifying, so genuinely exciting rather than just depressing. Physics has not entirely closed the door. Not entirely. There are legitimate, peer-reviewed, mathematically consistent frameworks within Einstein's own theory of general relativity that appear, on paper at least, to allow for travel that circumvents the light speed limit. There are real physicists, working at real institutions, publishing in real journals, exploring these ideas right now. This isn't fringe science. This isn't wishful thinking. This is hard physics grappling with the deepest question humanity has ever asked. Are we really stuck here forever? Or is there a way out? That's what this video's about. Before we continue, please subscribe to my channel so we can keep make videos like this. Thanks guys. We're going to start from the very beginning. What light is, why its speed is a limit at all, what Einstein actually said, and work our way through every serious proposal physicists have ever made for getting around that limit. Wormholes, warp drives, quantum entanglement, exotic matter, tachyons. We're going to look at what the real science says, what's genuinely possible in theory, what's almost certainly impossible in practice, and what remains genuinely, thrillingly unknown. By the end, you're going to understand this subject better than most people ever will, and you're going to feel the full weight of both sides of it, the wonder of what might be possible, and the deep, strange truth of what physics is actually telling us about the universe we live in. Let's start with light itself, because before we can talk about breaking the speed limit, we need to understand why there's a speed limit at all. And that story begins not with Einstein, though he'll get there, but with a Scottish physicist named James Clerk Maxwell, a set of equations so beautiful they reportedly made Einstein weep, and a 19th century experiment that accidentally broke Newtonian physics. The year is 1865. Maxwell publishes his treatise on electricity and magnetism. In it he unifies everything humanity knew about electric and magnetic phenomena into 4 elegant equations. These equations describe how electric fields create magnetic fields, how magnetic fields create electric fields, how disturbances propagate through those fields, and buried inside them, like a secret written in the mathematics, is a number: the speed at which electromagnetic waves travel through space. Maxwell calculated it from constants he'd measured in his lab, the permittivity and permeability of free space. He got 310,740,000 meters per second, and he noticed, with what must have been a shiver of recognition, that this was almost exactly the speed of light as measured by astronomers. He wrote, "We can scarcely avoid the conclusion that light consists in the transverse undulations of the same medium which is the cause of electric and magnetic phenomena. Light wasn't a separate thing. Light was an electromagnetic wave, and Maxwell's equations predicted its speed from first principles without any measurement of light itself. But there was a problem, a quiet, nagging, physics-destroying problem. In Newtonian mechanics, which had governed physics for 200 years, the speed of anything depended on the reference frame. If you're on a train going 100 km per hour and you throw a ball forward at 50 km per hour, someone standing on the platform sees the ball moving at 150 km per hour. Velocities add. This is obvious. This is intuitive. This is how the world works. But Maxwell's equations didn't have a reference frame. They just said, electromagnetic waves travel at c, that number, that constant, 3 times 10 to the 8th power meters per second, not 3 times 10 to the 8th power relative to anything, just 3 times 10 to the 8th power, which is absurd. Relative to what? Relative to the observer? But then Maxwell's equations would look different to different observers moving at different speeds. That violated a deep principle, that the laws of physics should be the same for everyone. The solution physicists reached for was the ether, an invisible medium filling all of space, absolute and stationary, relative to which light always travelled at c. The way sound waves travel through air, light waves would travel through ether. And different observers would measure different speeds of light depending on how fast they were moving through the ether. This was comforting. This fit the existing framework. And it turned out to be completely, disastrously wrong. In 1887, Albert Michelson and Edward Morley built an extraordinarily sensitive instrument, an interferometer, designed to detect Earth's motion through the ether. As Earth orbits the Sun, it must be moving through the ether in some direction. At some points in its orbit it should be moving with the ether wind, at other points against it, and the speed of light should be slightly different in each case. They measured again. They rotated their apparatus, they checked their equipment, they ran the experiment over months, at different times of year, in different orientations. The speed of light was exactly the same in every direction, every time, always c, always 299,792,458 meters per second. The ether didn't exist, and with it, the entire conceptual framework of 200 years of physics began to crack. The universe was telling them something they weren't ready to hear. The speed of light is not relative to anything. It is a constant of nature, invariant, absolute, the same for every observer in every state of motion everywhere in the universe. Someone standing still measures c, someone moving at half the speed of light measures c. Someone moving at 99% the speed of light in any direction still measures c. The speed of light doesn't add or subtract. It doesn't follow the rules of velocities. It just is. This was the crisis that handed a 26-year-old patent clerk in Bern the greatest opportunity in the history of science. His name, of course, was Albert Einstein, and his answer to the Michelson-Morley problem would rewrite our understanding of space, time, energy, and everything. But we'll get to that in a moment. First, let's linger on why c matters so fundamentally, not just as a cosmic speed limit, but as something woven into the structure of reality itself. The reason light travels at c isn't arbitrary. It isn't that light happens to be fast. It's that c appears in the relationship between electricity and magnetism. It's a ratio of fundamental constants of nature. When Maxwell's equations say light travels at c, they're not describing a property of light. They're describing a property of space and time. C is the conversion factor between space and time. It's the exchange rate between a meter and a second. It's baked into the geometry of the universe at the most fundamental level. This is why you can't just go faster. You're not running up against a wall. You're running up against the shape of reality itself. And Einstein, thinking about what that shape looked like from the inside, discovered something that should make your head swim every time you really sit with it. Space and time aren't separate things. They're one thing, a single, four-dimensional fabric, and c is the number that converts between the spatial dimensions and the temporal one. Everything, you, me, every particle in the cosmos, is always moving through this fabric at exactly c. Always, without exception. The catch is that you're distributing that motion between the space directions and the time direction. When you're sitting still in space, all your c of motion is going through time. You're aging at maximum rate, time ticking away at full speed. When you move through space, you're diverting some of your c from the time direction into the space direction, so time slows down for you. And if you could somehow move through space at c, if you could divert all your motion from time into space, you would stop moving through time entirely. You would be frozen in time. A photon moving at c doesn't experience time at all. From the photon's perspective, if it had one, it leaves its source and arrives at its destination in exactly 0 time. The universe, from the photon's point of view, has 0 thickness. This is what the speed of light actually means. It's not just fast, it's the boundary between having a time dimension and not having one. And this is why crossing it doesn't just require a lot of energy or a better engine. Crossing it requires something that, as far as we can tell, is physically impossible, becoming something that has no time dimension, or finding a way around the rules entirely, which is where it gets interesting. Let's establish what we're actually working with, because when people say the speed of light, they're often thinking of it as a practical barrier, like the sound barrier was, back before Chuck Yeager punched through it in 1947. A wall that feels insurmountable until you build something powerful enough to overcome it. But that's the wrong mental model. The speed of light isn't a wall. It's something far stranger and more fundamental. And to understand why, we need to understand what Einstein actually said in 1905, what his special theory of relativity actually claims, because most people have heard the words without grasping the full, brain-melting depth of what they mean. Einstein started with 2 postulates, 2 simple statements that, taken together, unravel everything. Postulate 1. The laws of physics are the same in all inertial reference frames. An inertial reference frame is just a frame that isn't accelerating. It's moving at a constant velocity or sitting still. Einstein says, pick any such frame, and the laws of physics look exactly the same. There's no experiment you can do inside a sealed box that will tell you whether you're moving or not. Motion is relative. There's no absolute rest. Postulate 2. The speed of light in a vacuum is the same for all observers, regardless of the motion of the light source or the observer. This is the one that wrecks everything. Put these 2 postulates together and follow the math wherever it leads, which Einstein did with terrifying rigor, and you get results so strange that most physicists of the time assumed he'd made an error. He hadn't. Every prediction his theory made has been confirmed by experiment, every single one, to extraordinary precision. So what does it actually say? The first consequence: time is not universal. There is no cosmic clock ticking away in the background, measuring absolute time for everyone equally. Instead, time is personal. It belongs to each observer and their particular state of motion. If you're moving relative to me, your clock runs slower than mine, not because of a mechanical effect, not because motion shakes the gears, but because time itself, for you, is passing more slowly. This is called time dilation, and the amount of dilation is described by the Lorentz factor, gamma, which equals 1 divided by the square root of 1 minus v squared over c squared. Let's make this concrete. At 10% the speed of light, the time dilation effect is tiny, less than 0.5%. Your clock and my clock almost agree. At 50% the speed of light, the effect gets meaningful. Your clock runs at about 87% of my rate. For every hour that passes for me, only 52 minutes pass for you. At 90% the speed of light, your clock runs at 44% of mine. You age less than half as fast as I do. At 99% the speed of light, your clock runs at about 14% of mine. You age 7 times slower. At 99.9%, it's 4.5%. You age 22 times slower. At 99.9999999%, the dilation is so extreme that a year of travel for you corresponds to thousands of years on Earth. As v approaches c, the Lorentz factor approaches infinity. Time dilation becomes infinite. Your clock, from my perspective, would slow to an absolute standstill. To reach c, you would need infinite time dilation. Time would have to stop for you entirely. That's not something that can be achieved with more fuel. It requires becoming something that doesn't experience time at all. This has been experimentally confirmed, by the way, not just theoretically predicted, actually measured. Muons are subatomic particles created when cosmic rays hit our upper atmosphere. They're unstable. They decay in about 2.2 microseconds. Even at nearly the speed of light, they should only travel about 660 meters before decaying. But we detect them at Earth's surface, having traveled through 15 kilometers of atmosphere. How? Time dilation. From the muon's perspective, its clock is ticking normally, and it decays in 2.2 microseconds. But from our perspective, the muon's internal clock is running so slowly, because it's moving at 99.7% the speed of light, that those 2.2 microseconds of muon time correspond to about 40 microseconds of our time. Plenty of time to reach the surface. The muon is not confused. The muon is not fooled by an illusion. For the muon, this is what time actually does. We've also confirmed time dilation with atomic clocks. In 1971, physicists Haffel and Keating flew ultra-precise atomic clocks around the world on commercial airlines and compared them to identical clocks that stayed on the ground. The flying clocks ran slightly slower, exactly as relativity predicted. We do this routinely now. GPS satellites require relativistic corrections to their clocks, or your navigation would drift by kilometers per day. Relativity isn't theoretical anymore, it's engineering. The second consequence: moving objects are shorter in the direction of motion. If you're flying past me at 90% the speed of light, your spacecraft, in the direction you're traveling, is compressed to 44% of its rest length. From my perspective. From your perspective inside the ship, everything looks normal. You're the one sitting still, remember? This effect is called length contraction, and it's equally real and equally weird. A spacecraft traveling at 99.9999%. The speed of light would be flattened, in the travel direction, to about 0.1% of its rest length. Thousands of light years of travel distance from the ship's frame of reference would be squashed down to something manageable. This is actually what makes relativistic travel conceptually possible for human lifespans, even without breaking the speed limit. If you travel at 99.9999% the speed of light, the 25,000 light years to the galactic center shrinks, from your perspective, to about 25 light years. At just under c, you'd cross it in just over 25 years of your time. Earth time, meanwhile, would have advanced 25,000 years. You'd arrive at the center of the galaxy without aging much, but everyone you know would be long dead. The third consequence is the most directly relevant to the question of faster-than-light travel, and it's the most decisive argument against it. Einstein showed that the energy required to accelerate a massive object increases with velocity, not linearly, but according to that same Lorentz factor. The relativistic kinetic energy of a moving object is gamma minus 1 times mc squared. As v approaches c, gamma approaches infinity, so the energy required approaches infinity. Put simply, to accelerate any object with mass to the speed of light requires infinite energy. An infinite amount, not a lot of energy, not more energy than we currently have access to. Infinite energy. This is not an engineering problem. It's not something we solve with a better reactor. You cannot reach the speed of light because doing so would require an infinite quantity of something that, by definition, cannot be infinite. Only massless particles, photons, and possibly gluons, can travel at c, precisely because the same formula, applied to zero mass, doesn't produce the infinity. They don't get accelerated to c. They are born at c and exist only at c. So that's what we're up against. Not a wall. A mathematical impossibility that emerges from the fundamental structure of space-time, and yet Einstein's framework contains loopholes, not in the sense of exploiting technicalities, in the sense that the mathematics itself, under certain interpretations and with certain assumptions lifted, admits configurations that sidestep the light speed limit without violating the core equations. Because special relativity, the theory we've been discussing, describes flat space-time. It describes physics in the absence of gravity, in the absence of curved space. The Lorentz factor and the energy barrier apply to objects moving through space. But what if you didn't move through space? What if space itself moved? That's the domain of general relativity, and that's where the really interesting ideas live. Before we get there, though, let's spend some time with something that doesn't get discussed enough. What it would actually feel like, physically and experientially, to push toward the speed of light. What would happen to you and your spacecraft as you approach that boundary? Because it's not just time dilation and length contraction. The universe, it turns out, becomes a genuinely hostile place when you try to rush through it. The experience of near light speed. Imagine you've built a ship. Perfect ship. Constant 1g acceleration. Exactly Earth gravity, comfortable, sustainable. You barely feel like you're in space. You point it toward Proxima Centauri, 4.24 light-years away, and you fire the engines. For the first year, you accelerate. Gradually, the stars ahead of you begin to blue shift, their light squeezing to shorter wavelengths as you rush toward them. The stars behind you redshift, stretching to longer, redder wavelengths, dimming. Nothing dramatic yet. By the end of year 1, you're travelling at about 77% of the speed of light. Now things start getting strange. The blue-shifted light ahead of you is getting more intense. Stars that were in the infrared are now visible. Stars that were visible are moving toward ultraviolet. The cosmic microwave background, the faint afterglow of the Big Bang, barely detectable at slow speeds, is blue-shifting into the radio spectrum, then into microwaves, then into light you can see, then into ultraviolet. By year 2, you're at 97% of C. The sky has done something bizarre. The stars have crowded together into a bright ring ahead of you, an effect called aberration. Your motion is squeezing all the light from ahead into a tighter and tighter cone. The universe looks like it's funneling into a bright spot in front of you. The circle of starlight around you is intensely blue-shifted. Ultraviolet radiation is now a serious concern for anything outside the ship's shielding. At 99% of C by year 3 of your trip, the situation has become genuinely dangerous in ways people don't often consider. The interstellar medium is not empty. It contains, on average, about 1 hydrogen atom per cubic centimetre. This is an extraordinarily low density, far better vacuum than anything we can create in a lab on Earth. But at 99% the speed of light, those atoms are hitting your spacecraft not like stray dust but like radiation. Each hydrogen atom from your frame of reference has the kinetic energy of a fast neutron in a nuclear reactor. They're ionizing radiation, bombarding your hull constantly, generating secondary radiation, depositing dose after dose in everything aboard. The cosmic microwave background from your frame of reference has now blue-shifted all the way up to hard X-rays. You're flying through what amounts to an X-ray bath. At 99.9% of C, the CMB has become gamma radiation. Individual hydrogen atoms, when they impact the hull, deliver energy comparable to a proton in a particle accelerator. The radiation environment inside the ship is now lethal without serious shielding. Orders of magnitude more radiation than the worst solar particle event ever recorded. and you still haven't even reached the halfway point of your journey. This is the practical reason why near-light speed travel is so much harder than it sounds even when you've solved the energy problem. You need shielding against ever more blue-shifted cosmic radiation. You need deflection systems for interstellar hydrogen that's effectively become a particle beam aimed at your hull. You need navigation systems that function when the visible universe has been optically distorted into an unrecognizable pattern ahead of you. None of this is impossible in principle. Physicists and engineers who think seriously about interstellar travel propose things like electromagnetic deflector shields, magnetospheres that push charged particles aside, and layered shielding of hydrogen, polyethylene, and liquid water. But all of these systems add mass, and mass makes the energy requirements worse, which requires more fuel, which adds more mass. The engineering cascade of near-light speed travel is humbling, which is why the ideas that don't involve moving through space at all, the wormholes, the warp drives, are so conceptually appealing. You're not trying to go faster than light, you're trying to make the distance smaller, or take a shortcut, or move the finish line closer. And relativity, strangely, does not obviously forbid that. To understand why FTL travel seems forbidden, and why some people think there might be ways around it, you have to deeply understand what special relativity is actually saying about the structure of the universe. Not the simplified version. The full, philosophically unsettling version that Einstein spent a decade working out after 1905. Let's start with simultaneity, or rather the lack of it. Here is a fact that most people have never fully absorbed. There is no universal now. Events that are simultaneous for one observer are not simultaneous for another observer moving relative to the first. This is not a perceptual illusion. It is not about light travel time creating an illusion of simultaneity. It is a fundamental feature of space-time itself. Here's the thought experiment Einstein used to demonstrate this. Imagine a train car traveling at high speed. There are lightning bolts that strike both ends of the train car simultaneously, that is, at the same moment, from the perspective of someone standing on the embankment, exactly in the middle of the train, watching it go by. Now, there's also an observer in the exact middle of the train car. The lightning bolts strike the two ends at the same moment, from the embankment observer's view. The light from both strikes travels toward the train observer, but the train observer is moving toward the front strike, and thus toward the photons from that strike, and away from the rear strike, so the light from the front reaches the train observer first. The embankment observer says, the strikes were simultaneous, and you received the front light first only because you moved toward it. The train observer says, I received the front light first because the front strike happened first. I'm in the middle of my own car. If the lights reached me at different times, the events happened at different times. Who's right? Both are right. In the embankment frame, the strikes are simultaneous. In the train frame, the front strike happened earlier. These are not errors of perception or communication. They are facts about two different inertial frames, and relativity tells us both frames are equally valid. There is no cosmic referee who can declare which frame has the true time. What this means, and this is the part that matters for FTL, is that before and after are not absolute. For events separated in space, whether A happens before B or B happens before A depends on your reference frame. There are some events that are causally connected, where a signal moving at c or slower could get from one to the other, for which all observers agree on the order. These are called time-like separated events, but there are other events so far apart in space that even a light signal couldn't get from one to the other in time, for which different observers disagree on the ordering. Some say A happened first, others say B happened first, others say they happened simultaneously. These are called space-like separated events. This is crucial. Space-like separation defines the boundary. Two events are space-like separated if the only way to get from one to the other is to move faster than light. And for space-like separated events, there is no agreed-upon causal order. Now here's the bomb. If you could send a signal faster than light, if FTL communication or travel were possible, you could always arrange things so that the signal arrives before it was sent. Not in some observer's frames, in all frames, because you can combine FTL motion with reference frame changes in a way that loops causality back on itself. This is called the tachyonic anti-telephone paradox, and we'll get into it in full detail later, but the key point for now is this. The light speed limit isn't just about preventing fast travel. It's about protecting causality. It's what keeps before and after from becoming meaningless. It's the reason the universe has a consistent history. When physicists say FTL travel violates causality, they mean it would make it possible to send information or matter backward in time. Not metaphorically, actually. And that opens up paradoxes that are not just philosophically uncomfortable, but logically self-contradictory. The deepest way to understand all of this is through the geometry of spacetime itself. Minkowski, a mathematician who was actually one of Einstein's former professors, reformulated special relativity in 1908 as the geometry of a four-dimensional space. 3 dimensions of space, 1 of time, combined into a single four-dimensional manifold called Minkowski spacetime. Einstein initially dismissed this as unnecessary mathematical complexity. He later admitted it was the key insight that led him to general relativity. In Minkowski spacetime, every event, every point in space at a moment in time, is a single point in the four-dimensional manifold. The history of any object is a curve through this space, its world line. The world line of a person sitting still is a vertical line in space, moving forward through time. The world line of someone moving is a tilted line. The speed of light defines a special structure in this geometry, the light cone. From any event, draw a cone forward in time, opening upward, and a cone backward in time, opening downward. The surface of the forward cone represents all the paths that light could take from this event. The interior of the forward cone represents all the paths that any massive object, anything slower than light, could take. Everything inside the forward light cone is the future of this event. Everyone, in any reference frame, agrees these events happen after the original event. Everything inside the backward light cone is the past. Everyone agrees these events happened before, but outside the light cone, the region space-like separated from the original event, that's where simultaneity breaks down. Whether those events are before or after depends entirely on the reference frame. There is no fact of the matter. Now, an FTL object, something that moves faster than light, would have a world line that lies outside the light cone, tilted at more than 45 degrees from the time axis in Minkowski's geometry. And here's the terrible thing. By choosing different reference frames, you can rotate that world line until it appears to slope backward in time. An FTL particle from some valid reference frame is a particle moving backwards in time. This is not a metaphor. It is a direct consequence of the Lorentz transformation that relates different reference frames. FTL motion and backwards time travel are the same thing, disguised by a change of reference frame. We'll come back to this when we talk about tachyons. For now, the point is, the prohibition on FTL travel isn't an arbitrary rule. It's the enforcement mechanism for causality. It's what prevents the universe from being logically incoherent. And yet, here's where it gets really subtle. General relativity, the extension of this framework to include gravity and curved spacetime, has a loophole. A very strange and specific loophole, the general relativistic exception. Special relativity applies to flat spacetime. It applies to observers in inertial frames that aren't accelerating, in spacetime that isn't curved by gravity. The prohibition on FTL motion applies in this context. You can't move a massive object through flat spacetime at the speed of light, let alone faster. But general relativity describes curved spacetime, and in curved spacetime the local prohibition still applies. At any given point locally nothing moves faster than light, but globally, across the whole curved manifold, things can look very different. Here's a simple example that everyone has encountered without realizing it. The universe is expanding, galaxies are moving away from us, and the farther they are, the faster they're moving. Galaxies beyond a certain distance, the Hubble radius, about 14.5 billion light-years, are moving away from us faster than the speed of light. No, really. The light from those galaxies will never reach us. They're receding faster than light can chase them. Is this a violation of special relativity? No, because those galaxies aren't moving through space at faster than light. Space itself is expanding. The space between us and those galaxies is growing. The galaxies are locally sitting relatively still in their local patch of space. It's just that the patch is getting further and further from our patch, because space itself is inflating. The distinction is subtle but crucial, moving through space versus space itself moving. Special relativity prohibits the former. General relativity says the latter is perfectly fine. This is the loophole. This is the crack in the door. What if we could somehow get space-time to move in a way that carried us from one place to another without us ever locally exceeding c? What if, instead of trying to fly through space at impossible speeds, we could take shortcuts through the geometry of space-time itself? This is the conceptual foundation of both wormholes and the Alcubierre warp drive. And we're going to explore both in serious detail. But first, let's make sure we've really understood something about what Einstein's theories say, because there's a misconception that floats around popular science that needs to be cleared up directly. People often say, Einstein's theories forbid faster-than-light travel, and that's true, in the context of special relativity, for massive objects moving through flat space-time. But what Einstein's general relativity actually does is more subtle. It provides a framework, the Einstein field equations, that relates the geometry of space-time to the distribution of matter and energy within it. And those equations admit solutions, valid mathematical solutions, that describe space-time geometries containing wormholes and space-time geometries containing warp drive-like structures. These solutions are not obviously forbidden. They're solutions to Einstein's own equations. The question, the really hard question, is whether those solutions are physically realizable. Whether the matter and energy distributions required to produce those geometries can actually exist in the universe. Whether the engineering is possible, not just the mathematics. And that question does not yet have a definitive answer. Forget the equations for a moment. Forget gamma and Lorentz transformations and Minkowski diagrams. Let's put you in the cockpit of a relativistic ship and just watch what happens. You're leaving Earth. The engines fire and you start to accelerate. At 1 g of acceleration, comfortable, sustainable, the same force as Earth's gravity, you'd reach 10% of the speed of light in about 35 days. Nothing too dramatic yet. The stars are still where they should be. Instruments show normal function. You might notice a very slight blue shift if you look ahead. The stars in your forward direction seem marginally brighter, marginally more blue. A very slight reddening behind you, but nothing alarming. Continue accelerating. By day 70, you're at about 18% of C. By day 120, approaching 25%. The blue shift ahead is now noticeable. Stars in the forward hemisphere have shifted enough that some previously invisible objects, things emitting primarily in the infrared, are now emitting in the visible spectrum. You're seeing light that wasn't visible from Earth. Conversely, some stars that were visible are now so redshifted behind you that they've faded below visual range. 6 months in, you're at about 35% of C, time dilation has become measurable. Your clocks are running about 6% slower than Earth's. If you called home right now, accounting for signal travel time, you'd be having conversations with people who are aging very slightly faster than you. Not dramatically, just a little. 1 year in, you're at about 60% of C. Now things are getting genuinely strange. The phenomenon called aberration is becoming pronounced. Stars in the forward direction are crowding together. Your motion through space is changing the apparent angular positions of stars, squeezing them toward the direction of travel. Stars that should be 90 degrees off your bow have migrated to 60 degrees, 50 degrees, clustering toward the front of your field of view. The sky's beginning to look lopsided, brighter and more crowded ahead, dimmer and sparser behind. The Doppler shift is now dramatic. Many of the stars ahead of you have shifted from yellow or white into blue-white or ultraviolet. Some that were red stars are now green or yellow. The stellar population visible to your eye is completely different from what you'd see from Earth. You're looking at the same stars, but at entirely different wavelengths. 18 months in. You're at about 75% of C. The radiation environment is starting to become a concern. Here's something that catches people off guard when they think about relativistic travel. The interstellar medium, the gas and dust between stars, isn't empty. It contains about 1 hydrogen atom per cubic centimetre in the interstellar void. This is almost nothing by everyday standards, a better vacuum than any we can create in a laboratory. But at 75% of the speed of light, those hydrogen atoms are hitting your ship with significant energy. Each collision is in the energetic range of cosmic ray particles. The hull is constantly being bombarded. Without shielding, the cumulative radiation dose would become a serious health concern. With proper shielding, several meters of water, or equivalent, it's manageable, but now you're carrying a lot more mass, which means more fuel, which means you see the problem. Relativity doesn't just make going faster harder, it makes going fast at all a radiation management challenge. 2 years in, you're at roughly 86% of C. Time dilation is now 2 to 1. For every year you experience, Earth ages 2 years. You've aged 2 years. Earth has aged 4. The aberration of the starfield is now extreme. The entire visible universe has been squeezed into the forward hemisphere. Most of the stars are now in a circle of about 60 degrees around your direction of travel. Behind you, the sky is almost uniformly dark. The few stars visible there are so Doppler shifted into the infrared that they're barely detectable optically. The sky ahead blazes with stars that have all shifted into shorter wavelengths. And the cosmic microwave background, the faint 2.7 Kelvin radiation that bathes all of space, normally invisible to human eyes, has now blue shifted into the radio band, then microwave. Then, it's starting to approach the infrared. From your ship's frame, the CMB is hotter, much hotter. Because you're rushing headlong into it, the photons are hitting you, more energetically. 2.5 years, you're at 90% of C. Time dilation is at a factor of 2.3. The CMB, from your perspective, has blue shifted into the far infrared. It's actually warm, not dangerous but measurable. Your ship's thermal management systems are handling a radiation load that wouldn't exist at low speeds. 3 years. 95% of C, Lorentz factor, is about 3.2. 3 years of your life. Earth has aged almost 10. The aberration of the starfield has become spectacular. The entire universe ahead of you is compressed into a roughly 40-degree cone. Outside that cone is near darkness. Inside it is a blinding blue-white concentration of starlight, plus the CMB, which has now shifted into the near-infrared and is approaching visible light. The hydrogen atoms of the interstellar medium are now hitting your hull with energies comparable to protons in early particle accelerators. Without a magnetic deflector or substantial shielding, you'd be receiving a radiation dose that would be fatal over months. Even with shielding, cosmic ray production from the hull interactions is a non-negligible secondary hazard. 3.5 years. 99% of C. The Lorentz factor is 7.1. 7 years on Earth for every year you age. The starfield ahead has collapsed into a bright ring, like a bullseye, about 25 degrees from your forward direction. The center of that ring, the direction you're actually traveling, is an intense blue-white blaze. The CMB has shifted into visible light. You're being bathed in photons from the Big Bang, now blue shifted into something like sunlight. It's not quite enough to be dangerous, but it's there, measurably adding to your thermal load. The hydrogen in the interstellar medium is now delivering radiation doses comparable to serious nuclear accidents for anyone outside the shielding. Inside the shielded crew compartment, it's manageable, but the engineering challenges are severe. 4 years. 99.9% of C. Lorentz factor is 22. For every year you age, Earth ages 22 years. The universe ahead of you is a single blazing point of blue-white light, or nearly so. Aberration has compressed the entire forward hemisphere into a circle of perhaps 8 degrees. The CMB is now hard ultraviolet and soft X-rays. The hydrogen atoms of the interstellar medium are each carrying kinetic energy, equivalent to fast neutrons from a reactor, ionizing radiation, penetrating, relentless. Anyone outside the hull is dead within minutes, not from vacuum but from radiation. Anyone inside without serious shielding would receive a lethal dose in hours. With proper shielding, a substantial water or polyethylene barrier, or a strong magnetic deflector field, survival is possible, but this is a serious engineering constraint. You are approaching the conditions under which going faster becomes less about energy and more about surviving the journey at all. This section of the physics, the radiation environment of relativistic travel, is underappreciated in popular discussions of interstellar travel, which tend to focus on propulsion. But it may well be the more fundamental limiting factor for biological travelers. Robots and probes don't care about radiation. Humans do. And none of this changes the fundamental energy problem. At 99.9% of C, your ship, if it masses 1,000 metric tons at rest, has a kinetic energy of about 22 times, 1,000 times C squared equals 22 petajoules of kinetic energy. That's roughly 5,000 Hiroshima bombs of energy just to be moving at that speed. Getting to 99.99% requires about 7 times more. Getting to 99.999% requires about 22 times more than that. The energy cost of the last few decimal places of C is ferocious. And it never ends because the Lorentz factor diverges. It never reaches a maximum. It just keeps climbing as you approach c. You're always spending more for a smaller gain in actual speed. The speed of light is an asymptote. You approach it but never reach it. And the approach itself becomes exponentially more expensive the closer you get. This is why the search for FTL isn't crazy, it's rational. The alternative, brute force relativistic travel, is so costly, so hazardous, so punishing in every dimension that finding a better route isn't wishful thinking, it's engineering good sense. So let's talk about the better routes. Let's talk about folding space. In 1935, Albert Einstein was sitting in his office at the Institute for Advanced Study in Princeton, doing what Albert Einstein did, reworking the mathematics of general relativity and looking for things he might have missed. He wasn't alone. Working with him was Nathan Rosen, a young physicist from Brooklyn who was serving as Einstein's assistant. Together they were examining the mathematics of the simplest possible black hole solution, the Schwarzschild solution, which describes the space-time geometry around a perfectly spherical, non-rotating, uncharged mass. What they found was strange. The Schwarzschild solution, when you push the mathematics all the way to its logical conclusion, past the event horizon into the center of the black hole, doesn't describe a point singularity surrounded by an inescapable shell. It describes something that looks, topologically, like a bridge, a tunnel connecting two separate regions of space-time. In the geometry of the solution, if you could somehow enter the black hole and navigate through it, you would emerge in somewhere else. Not necessarily somewhere else in our universe, possibly a different universe entirely, or a different region of our own space-time so remote that you'd never reach it by ordinary travel. Einstein and Rosen called this structure a bridge. We now call it an Einstein-Rosen bridge. Popular science knows it as a wormhole. On paper, the mathematics is clean and beautiful. Two regions of space-time connected by a tube. Go in one end, come out the other. If you could position the two mouths of the wormhole at useful locations, say Earth and Alpha Centauri, you could walk through in minutes, regardless of the actual spatial distance. There's just one problem, actually several, the Schwarzschild wormhole problem. The original Einstein-Rosen bridge, the one you get in the Schwarzschild solution, is not traversable, not even in principle. Here's why. The bridge forms, mathematically, inside the event horizon of a black hole. But the interior of a black hole has a deeply strange property. The radial direction, inside the event horizon, becomes time-like. Not a direction in space anymore, a direction in time. Specifically, the direction toward the singularity is the future. It is not a place you can go. It is a time you will inevitably reach, in the same way you will inevitably reach tomorrow. Inside a Schwarzschild black hole, the singularity isn't at the center in space. It's in the future. Every world line, every path forward in time leads to it. There's no way to avoid it, because avoiding the future is impossible. The Einstein-Rosen bridge connects to another universe. Yes, but only through a path that goes through the singularity, through the time-like direction that everything inside the horizon is inevitably dragged toward. The bridge forms and then pinches off in a time so short that even light cannot traverse it. It snaps shut before anything can get through. An observer falling into the black hole and an observer in the hypothetical other universe on the other side cannot communicate, even in principle. The bridge is not traversable. It's a mathematical curiosity, not a transit route. For decades, this seemed to close the door on wormholes as useful objects. Yes, they exist in the mathematics. No, you can't use them. Morris and Thorne, the traversable wormhole. Then, in 1988, something changed. Kip Thorne, one of the most respected relativists in the world, who would later win the Nobel Prize for his work on gravitational waves, was approached by his friend Carl Sagan. Sagan was writing a novel about first contact. The novel was Contact, and he wanted to know, is there any physically plausible mechanism by which a character could travel enormous distances instantaneously? Something that didn't obviously violate known physics. Thorne took the question seriously. He assigned it to his graduate student Michael Morris, and together, Morris and Thorne did something clever. They reversed the usual approach. Instead of starting with a matter distribution and asking what space-time geometry it produces, they started with a space-time geometry that allowed traversable wormholes and asked what matter distribution would be required to produce it. The answer was exotic matter, specifically matter with negative energy density. Matter that, in the region of the wormhole throat, exerts a gravitational effect opposite to ordinary matter. It repels rather than attracts. It holds the wormhole open. It prevents the throat from collapsing. This is called exotic matter, and its key property, negative energy density, seems to violate our intuitions about what matter is. Mass is supposed to be positive. Energy is supposed to be positive. Something with negative energy density is deeply strange. But here's the critical point. Negative energy density is not obviously forbidden by quantum mechanics. In fact, we know it can exist. The Casimir effect and negative energy. In 1948, the Dutch physicist Hendrik Casimir predicted that two uncharged metal plates, placed very close together in a perfect vacuum, would experience a force pushing them together. Not because of any electromagnetic interaction, because of the quantum vacuum. The vacuum isn't empty. Quantum field theory says it's filled with fluctuating fields, with virtual particles appearing and disappearing, with a baseline of energy that permeates all of space, the vacuum energy. Between two very closely spaced plates, only quantum modes with wavelengths that fit between the plates can exist. Outside the plates, all modes can exist. This means there are more vacuum fluctuations outside the plates than inside. The asymmetry produces a pressure, the Casimir force, pushing the plates together. The Casimir effect has been experimentally confirmed. It's real. You can measure it. And the region between the plates, the region where the vacuum modes are restricted, has a lower energy density than the surrounding vacuum, lower than nothing. Negative energy density, not much, not nearly enough to hold open a wormhole, but in principle, negative energy density can exist because we've observed it. Other quantum mechanical effects, squeeze states of light for instance, can also produce regions of negative energy density. These are small effects, delicate and difficult to maintain, but they're real. This gives the Morris Thorne traversable wormhole a fighting chance at physical plausibility. The question is, can you get enough exotic matter with sufficiently negative energy density concentrated over a large enough region to hold a traversable wormhole open long enough to use it? And the honest answer is, we have no idea. We can't even make a confident estimate. The quantities involved are so far beyond anything we know how to produce that we can't even say whether they're in principle achievable or not. The stability problem. Even setting aside exotic matter, traversable wormholes face another deep problem: stability. Small perturbations to a wormhole geometry, the vibrations of someone walking through it, the radiation they emit, quantum fluctuations, tend to amplify over time. The feedback loop is positive. Perturbations make the wormhole geometry more perturbed, which makes the feedback stronger, which destroys the wormhole in a catastrophic pinch-off. You need the exotic matter not just to hold the throat open in equilibrium, but to actively suppress these instabilities. Controlling the negative energy density dynamically, in response to perturbations in real time, is an engineering challenge so far beyond anything we know how to do that it might as well be magic. The chronology protection conjecture. Then there's Stephen Hawking. Hawking looked at traversable wormholes and noticed something very uncomfortable. If you have a traversable wormhole connecting 2 points in space, you can, by accelerating one of the mouths or by exploiting time dilation effects, turn it into a time machine. Here's how. Start with a traversable wormhole connecting 2 locations in space. Leave one mouth, call it A, stationary. Take the other mouth, B, on a relativistic trip. Accelerate it to near light speed, travel for a while, then return. Because of time dilation, the moving mouth ages less than the stationary mouth. Now, when you look through the wormhole, you're looking across a time gap. The 2 mouths exist at different moments in their respective histories. If the time gap is large enough, and you position the mouths appropriately, you can walk through the wormhole and emerge in the past. From there, you can send a message or an object or yourself to a time before the wormhole was created. Hawking found this deeply disturbing and proposed the chronology protection conjecture, that the laws of physics conspire to prevent the formation of closed time-like curves, loops in space-time that allow travel into the past. He suspected that quantum effects, which his calculations suggested would cause radiation to diverge catastrophically at the moment a time machine forms, would always destroy it before it could be used. This is a conjecture. It hasn't been proven. It's physically motivated. There are theoretical reasons to think it holds. But it's not a theorem. We don't fully understand quantum gravity well enough to say definitively whether Hawking's conjecture is correct. ER equals EPR, wormholes and quantum entanglement. In 2013, theoretical physicists Juan Maldacena and Leonard Susskind proposed something that may be the most profound idea in fundamental physics of the 21st century so far. They suggested that Einstein-Rosen bridges, wormholes, and Einstein-Podolsky-Rosen pairs, quantum entanglement, are the same thing. The conjecture is expressed as ER equals EPR. The idea is this: when two particles are quantum entangled, they are not just correlated in the sense of sharing information. They are geometrically connected through a tiny microscopic wormhole, an Einstein-Rosen bridge at the quantum level. The non-local correlations of entanglement are the physical signature of this geometric connection. If this is correct, it would mean that entanglement and wormholes are aspects of the same phenomenon, that the geometry of space-time and the entanglement structure of quantum mechanics are deeply intertwined. It would be a hint toward the long-sought theory of quantum gravity, the unification of general relativity and quantum mechanics. It would also mean that wormholes aren't exotic, hypothetical structures that might exist in principle if we could gather enough exotic matter. They'd be ubiquitous, appearing naturally in the quantum structure of space-time, woven into the fabric of reality at the Planck scale. The challenge, of course, is that a Planck scale wormhole is unimaginably small. The Planck length is about 10 to the power of minus 35 meters. The nucleus of an atom is about 10 to the power of minus 15 meters. The Planck scale is 20 orders of magnitude smaller than an atomic nucleus. A wormhole at that scale is utterly useless for transportation, but the conjecture suggests a deep connection between the geometry of space-time and quantum information, and exploring that connection might eventually tell us whether macroscopic wormholes are achievable, or whether the Planck scale versions are all there are. Wormholes, in summary, are mathematically well-defined, theoretically possible within general relativity, deeply connected to unresolved questions in quantum gravity, almost certainly impossible to construct with known physics, and not definitively ruled out by any known law, which is exactly the kind of ambiguous, frustrating, exhilarating status that makes them so fascinating. In 1994, a young Mexican physicist named Miguel Alcubierre was watching Star Trek. This is literally how the paper is described in physics circles, though Alcubierre himself tells it slightly differently. He was a PhD student at Cardiff University, thinking about general relativity, when he wondered whether the warp drive from science fiction had any basis in actual physics, not as a metaphor, as a technical possibility. He sat down with the Einstein field equations, the same equations Einstein had written down in 1915 to describe the relationship between matter, energy, and space-time curvature, and he asked, is there any geometry of space-time that would allow an object to travel from point A to point B faster than light would take, without violating special relativity? He found one, and when he published it in the journal Classical and Quantum Gravity, it caused a sensation. The Alcubierre metric. The technical description is called the Alcubierre metric, and what it describes is this. Imagine a region of flat space-time, normal, uncurved space, the kind described by special relativity, shaped like a bubble. Inside the bubble is the spacecraft. The bubble itself is surrounded by a region of distorted space-time, a warp field that compresses space in front of the bubble and expands space behind it. The ship inside the bubble isn't moving through space, it's sitting still in its own local flat bubble. The bubble is moving through space. But here's the key. The bubble can move through space faster than light, and this doesn't violate special relativity. Because what's moving faster than light is the geometry of space-time itself, not an object moving through that space-time. Remember the expanding universe? Distant galaxies can recede faster than light because space is expanding. This is the same principle. The ship inside the bubble at every moment is sitting still in its local space-time. Locally, nothing is moving faster than light, but globally, across the whole curved manifold, the ship travels from A to B in less time than light would take travelling through flat space. This is genuinely, legitimately consistent with general relativity. The Alcubierre metric is an exact solution to the Einstein field equations. The math works. The physics, in terms of internal consistency, is sound. Alcubierre calculated that a ship using his warp drive could, in principle, travel to a star 10 light-years away in any arbitrary amount of time, a week, a day, an hour. The geometry of the warp field determines the speed, and that geometry is not locally constrained to be below c. He published. The physics community read it. And then they started finding the problems. The exotic matter problem. Here's the first and largest problem. The Alcubierre warp drive requires exotic matter. Like the Morris-Thorne wormhole, the warp field geometry requires regions where the energy density is negative. More specifically, it requires a shell of exotic matter, matter with negative energy, wrapped around the spacecraft to produce the compression and expansion of spacetime needed for the warp field. How much exotic matter? In Alcubierre's original 1994 paper, the amount required was roughly the equivalent of Jupiter's mass, but in negative energy. That's 2 × 10 to the 27th kilograms of exotic matter, with negative energy density. We have never produced a detectable quantity of exotic matter. The Casimir effect produces negative energy densities, yes, but on the scale of the gap between 2 closely spaced metal plates, fantastically small quantities. The extrapolation from "we've detected Casimir-scale negative energy" to "we can produce Jupiter masses of it" is approximately infinite. But wait, the story gets more interesting. Harold White's modification. In 2012, Harold White, a physicist at NASA's Johnson Space Center, proposed a modification to the Alcubierre geometry that dramatically reduced the exotic matter requirements. Alcubierre's original metric assumed a particular shape for the warp bubble, roughly spherical, with the field concentrated in a thin shell. White argued that by changing the shape of the bubble, thickening the ring of field, changing its oscillation pattern, the exotic matter requirements could be reduced by orders of magnitude. In his calculations, White got the exotic matter requirement down from Jupiter mass to something on the order of 500 kilograms. Still exotic, still negative energy, but no longer planetary in scale. White then set up a small experiment at Johnson Space Center, the White-Jude Warp Field Interferometer, attempting to detect a tiny warp field produced by a small energy concentration. The experiment produced results that White initially interpreted as suggestive of a spacetime distortion, though most physicists were skeptical, and subsequent analysis suggested the effect was likely an artifact. The experiment was quietly discontinued. But White's theoretical work, the idea that the geometry of the warp bubble could be optimized to dramatically reduce exotic matter requirements, remains in the literature and continues to influence the field. The Bobrick-Martyr framework. In 2021, physicists Alexei Bobrick and Gianni Martius published a comprehensive framework for analyzing all possible warp drive spacetimes, not just Alcubierre's specific solution, but the entire class of geometries that might allow superluminal travel. Their paper, published in Classical and Quantum Gravity, was notable for several things. First, they showed that the entire class of superluminal warp drives, not just Alcubierre's, requires exotic matter with negative energy density. This was not obvious from previous work. There was hope that other warp geometries might avoid the requirement. Bobrick and Martyr showed that it's unavoidable for any geometry that achieves true superluminal transit. But second, and this is the surprising and underappreciated part, they showed that subluminal warp drives, ones that don't exceed the speed of light, don't necessarily require exotic matter. A positive energy warp bubble, moving at less than c, is theoretically consistent. This is actually significant. It means that even without solving the exotic matter problem, warp drive physics isn't entirely useless. A warp drive that travels at, say, 90% of the speed of light, significantly slower than the theoretical maximum but faster than any propulsion system we've ever built, might be achievable with positive energy matter configurations. Whether might be achievable will ever translate into can be built is another matter entirely. The controllability problem. Here's a problem with the Alcubierre drive that gets less attention than the exotic matter issue, but may be just as fundamental. How do you steer it? The ship is inside the warp bubble, in a region of flat spacetime, isolated from the surrounding spacetime by the warp field. The warp field is being generated by the exotic matter ring outside. To change course, you'd need to change the shape and orientation of the warp field. But any signals you send from inside the bubble have to travel through the bubble wall, through the warp field itself. In certain configurations of the Alcubierre drive, the interior of the bubble is causally disconnected from the front of the warp field. Light signals from the ship cannot reach the front of the warp field. You're sitting inside a space-time region that's moving through space, and you can't send signals to the part of it that's doing the driving. It's like being in a car where you can control the brake pedal, but not the steering wheel, and the steering wheel is in the trunk. A ship travelling in an Alcubierre bubble, in some configurations, cannot navigate itself. It was aimed before departure, and it will arrive wherever it was aimed, and that's that. This is not useful for actual transit. Various solutions have been proposed. Pre-programmed course corrections, manipulation of the bubble from the exterior, or different configurations of the metric that preserve causal contact between the ship and the warp field front. But none of these has been developed to the point of being a practical solution. The Hawking radiation problem. Then there's the radiation problem. Several physicists, including Stefano Finazzi, Stefano Liberati, and Carlos Barcelona, analysed what quantum field theory predicts would happen inside an Alcubierre warp bubble, and they found something troubling. The warp bubble concentrates and amplifies quantum vacuum fluctuations, the same fluctuations responsible for the Casimir effect and Hawking radiation from black holes. Inside the bubble, a high-energy radiation field builds up as the bubble moves faster. By the time the bubble reaches the speed of light, the radiation density inside has become extreme, potentially destroying the ship that the bubble was supposed to be protecting. This is similar to the mechanism by which black holes emit Hawking radiation, but the geometry is different enough that the analysis is complex and contested. Some follow-up papers reach different conclusions depending on the specific bubble configuration. The consensus is that quantum effects would produce some radiation inside a warp bubble, but whether it's catastrophic depends on parameters not yet pinned down. Where warp drive physics stands today, the honest summary is this. The Alcubierre warp drive is real physics in the sense that it's a valid mathematical solution to Einstein's equations. It's not obviously impossible in the sense that it doesn't contradict any fundamental law, but it requires exotic matter with negative energy density in quantities we have never come close to producing, solutions to serious stability and controllability problems that haven't been worked out, survival of the ship against quantum vacuum radiation that builds up inside the bubble, somehow not creating a time machine in the process, which warp drive geometries may do if used carelessly. None of these is proven impossible. All of them are, with current physics, utterly beyond our engineering capability. The field is real. The researchers working on it, at universities and in the small but active warp drive research community, are doing legitimate physics. But the gap between the mathematics and the engineering is vast, probably centuries wide if it's crossable at all. Still, the mathematics works, Einstein's equations allow it, and that's more than most people thought even 30 years ago. If there's one subject that generates more FTL confusion in the general public than any other, it's quantum entanglement. Barely a month goes by without a headline somewhere announcing that scientists have transmitted information faster than light using entangled particles, or that quantum teleportation offers a path to instant communication, or that entanglement proves Einstein wrong about the speed limit. None of this is true, and explaining why is actually a beautiful exercise in understanding what quantum mechanics is really saying about the nature of reality. Let's start from the beginning. What quantum entanglement actually is in quantum mechanics, particles don't have definite properties, like position, or spin orientation, or polarization, until those properties are measured. Before measurement, a particle exists in a superposition, a combination of multiple possible states simultaneously. When two particles interact in certain ways, they can become entangled. This means their quantum states are correlated in a way that cannot be described by treating them as independent particles. The state of the pair has to be described as a unified whole. The classic example, you produce two particles whose total spin must be zero. You send one particle to Alice in Tokyo and the other to Bob in Buenos Aires. Before anyone measures anything, neither particle has a definite spin direction. They're each in a superposition. Now Alice measures her particle. Let's say it comes up spin up. Instantly, in the same moment, Bob's particle must be spin down. Not will be measured as spin down, is spin down. The correlation is instantaneous regardless of the distance between Alice and Bob. Einstein found this deeply disturbing. In a famous 1935 paper with Boris Podolsky and Nathan Rosen, the EPR paper, he argued that this implied either that quantum mechanics was incomplete, there must be some hidden variables determining the outcomes in advance before measurement, or that something was happening that violated what he called local realism, the idea that distant events can't instantaneously affect each other. Einstein favoured the hidden variables explanation. He was wrong. In 1964, physicist John Bell derived a mathematical theorem that drew a decisive line between quantum mechanics and any hidden variable theory. He showed that the correlations predicted by quantum mechanics for certain experimental setups involving entangled particles are stronger than any hidden variable theory could produce, no matter how clever the hidden variables or how many of them you add. If you measure the spins of entangled particles along multiple different axes and tabulate the correlations between Alice's and Bob's results, quantum mechanics predicts specific numbers. Hidden variable theories predict different, less extreme numbers, and the difference is measurable. Experiments by Alain Aspect in the 1980s, and subsequent ever more refined experiments by many groups over the following decades, confirmed the quantum mechanical predictions. The correlations are exactly as strong as quantum mechanics says, and stronger than any local hidden variable theory can explain. This is not a matter of interpretation, it's a measured fact. The universe is non-local. Entangled particles are genuinely, non-trivially correlated across arbitrary distances, instantaneously. Einstein was wrong. The EPR effect is real, and the correlations really are instantaneous. So why can't you use this for FTL communication, the no communication theorem? Here's the catch, and it's subtle. When Alice measures her particle and gets spin up, she knows instantly that Bob's particle is spin down. But here's the crucial question. What does Bob's experience look like before Alice's measurement? Bob measures his particle, he gets a result, let's say spin down. But, and this is the key, Bob doesn't know whether he got spin down because Alice already measured spin up, or whether Alice hasn't measured yet, or whether Alice is even doing the experiment at all today, because Bob's particle, before Alice measures, would also have given spin down if measured. The quantum mechanics is set up so that Bob's local measurement statistics are exactly the same whether Alice has measured or not. Both before and after Alice's measurement, Bob sees a 50-50 distribution of spin up and spin down. He cannot tell from his measurement alone whether Alice has measured or not. The information that Alice measured, spin up, is not transmitted to Bob, because Bob can't read it in the statistics of his particle. To compare notes, to confirm the correlation, and see that Alice got spin up when Bob got spin down, Alice and Bob have to communicate. And that communication can only go at light speed or slower. The classical communication channel is unavoidable. This is the no communication theorem, and it's one of the most robustly proven results in all of quantum mechanics. It's not an engineering limitation. It's not. We haven't figured out how to extract the information yet. It's a mathematical proof that the structure of quantum mechanics prevents any information from being transmitted via entanglement correlations. Here's the intuition for why. Quantum measurement outcomes are random. When Alice measures her particle, she gets a random result. Spin up or spin down, 50-50. She cannot choose which result she gets, so she cannot encode information in her choice of outcome. Even if Bob's particle responds instantly, it's responding to a random event that Alice didn't control. There's nothing to read on Bob's end that he couldn't have gotten without Alice. To transmit a bit of information, you need to be able to choose, send a 1 or send a 0. But Alice can't choose what measurement outcome she gets. The randomness is fundamental, and the randomness seals the channel. But wait, you might be thinking, what about quantum teleportation? I've seen headlines about scientists teleporting photons or quantum states over enormous distances. Isn't that FTL? Quantum teleportation is real, and it's genuinely remarkable, but it doesn't transmit anything faster than light. Here's what quantum teleportation actually does. Alice has a quantum system in an unknown state that she wants to transmit to Bob. She and Bob share an entangled pair of particles. Alice performs a measurement on her system and her half of the entangled pair. This gives her a classical result, 2 bits of classical information. She sends these 2 classical bits to Bob via a conventional channel, radio, fiber optic, whatever. Bob uses those bits to perform an operation on his half of the entangled pair, transforming it into the state Alice wanted to transmit. The original quantum state has been teleported, but the process requires classical communication. The two classical bits travel through the conventional channel at light speed or slower. Without those bits, Bob has no idea what to do with his entangled particle. The teleportation is not instantaneous. It takes as long as the classical communication channel takes. What quantum teleportation achieves is genuinely amazing. It transmits an unknown quantum state without sending the physical particle that was in that state, and it does so without Bob ever knowing the intermediate state, which quantum mechanics doesn't even allow for unknown quantum states. It has genuine applications in quantum computing and quantum cryptography, but it cannot, transmit information faster than light. If entanglement doesn't enable FTL communication, what does it tell us? It tells us that the universe is, in a deep sense, non-local. Quantum correlations exist between distant particles that cannot be explained by any mechanism where information passes between them at finite speed. The correlations are just there, baked into the quantum state of the system. This suggests that our classical intuition about how reality works, where distant things are independent, where local causes produce local effects, where you have to send a signal to coordinate distant events, is fundamentally wrong. Reality is more connected than that. The universe doesn't store information in separate particles that occasionally interact. It stores it in joint quantum states that can span arbitrary distances. The entanglement is the connection. What this implies for the future of physics, whether, as the ER equals EPR conjecture suggests, this quantum non-locality is the fingerprint of spacetime connectivity at the Planck scale, is one of the most exciting open questions in all of science. But for FTL communication, the no communication theorem is a wall, a mathematical, irrefutable wall. Entanglement is a window that lets you see the non-local structure of reality, but it's a window you can't throw anything through. If you've spent any time in physics forums, you've probably encountered the concept of tachyons, hypothetical particles that always move faster than light. They're a staple of science fiction, showing up in everything from Star Trek to countless novels as a catch-all explanation for FTL communication and travel. But tachyons are also real physics. They're not just science fiction hand-waving, they emerge from actual attempts to generalize the mathematics of particles beyond the light speed limit. The story of tachyons is a story about what happens when you take mathematics seriously and follow it into uncomfortable territory. And the place it leads is genuinely strange. In special relativity, the energy, momentum, and rest mass of a particle are related by the equation E squared equals pc squared plus mc squared squared. This is the full relativistic energy-momentum relation, a generalization of the famous E equals mc squared. For ordinary particles, electrons, protons, neutrinos, the rest mass m is positive and real. The energy and momentum are real numbers. The Lorentz factor gamma equals 1 over the square root of 1 minus v squared over c squared is real for any v less than c, and undefined for v equals c or above. You cannot accelerate a positive mass particle to c. For photons, m equals 0. The energy-momentum relation gives E equals pc. They move at exactly c. They have no rest mass and no rest frame. But what if m squared is negative? What if the rest mass is imaginary? Not in the philosophical sense, but in the mathematical sense, a multiple of the square root of -1. Then the Lorentz factor becomes real again, but only for v greater than c, if m is imaginary. The Lorentz factor formula, which normally produces real values for v less than c, and imaginary values for v greater than c, does the reverse. It gives real, physical values only for speeds above c. A particle with imaginary mass cannot exist below the speed of light. It cannot exist at the speed of light. It can only exist above the speed of light, always faster than light, never slower. The speed of light is, for such a particle, a lower limit rather than an upper limit. These hypothetical particles were formally proposed by physicist Gerald Feinberg in 1967, who gave them the name tachyons, from the Greek word tachys, meaning swift. Particles slower than light are tardions. Particles at light speed are luxons, the photon is a luxon. Particles above light speed are tachyons. If tachyons existed and could interact with ordinary matter, you would have a problem, a very serious problem. The problem is called the tachyonic antitelephone, and it was formalized in 1970 by physicist Gregory Benford, who went on to become a prominent science fiction writer, and his collaborators. Here's the setup. You and a friend are travelling toward each other at some fraction of the speed of light. You have a tachyon transmitter. You send a tachyon message to your friend. Because tachyons move faster than light, the message arrives before a light signal would. But here's where the reference frame issue comes in. Remember that in special relativity, moving observers disagree about the timing of space-like separated events. For a sufficiently fast tachyon, in a reference frame moving at some velocity relative to the original, the message can arrive before it was sent. Your friend, in their reference frame, which is valid, because all inertial reference frames are valid, sees the tachyon message arrive before you sent it. They can reply with another tachyon message. Their reply can reach you before you sent the original message. By combining two FTL transmissions, one in your frame, one in your friend's frame, you've created a signal that travels backward in time. If you sent the message only if you received the reply, and you received the reply only if you sent the message, you have a causal loop, a logical contradiction. This is why tachyons, if they existed and interacted with ordinary matter in the naive way, would be causality destroying. Various escape routes have been proposed. The reinterpretation principle suggests that a tachyon moving backward in time is physically equivalent to an antitachyon moving forward in time. So the loop can be reinterpreted as a sequence of particle emissions and absorptions that's consistent. But this doesn't fully resolve the problem. It changes the description without removing the causal paradoxes. Here's where tachyons appear in real, current physics, not as FTL particles, but as a diagnostic tool. In quantum field theory, the mathematical framework that describes the standard model of particle physics, a tachyonic field, is a field whose particles, if you naively read the mass term, have imaginary mass. This would seem to indicate, FTL particles and broken causality everywhere. But the physics community, after some initial alarm, figured out what tachyonic fields actually mean in QFT. A tachyonic field doesn't describe particles that move faster than light. It describes an unstable configuration. The current state of the field is not at the minimum of the potential energy. It's sitting at an unstable maximum, like a ball balanced on the top of a hill. The imaginary mass term is telling you that the field will roll down from that unstable point to a stable minimum, releasing energy in the process. This process is called tachyon condensation, and it's a fundamental mechanism in quantum field theory. The Higgs boson was, in the early universe, a tachyonic field. The universe before the electroweak phase transition was in an unstable state with the Higgs field sitting at an unstable maximum. The phase transition, the Higgs field rolling to its true minimum, is what gave elementary particles their masses. In string theory, tachyons appear in the spectrum of strings and are interpreted as signals that you're analysing the wrong vacuum state. The mathematical description is sitting at an unstable point, and the correct ground state has no tachyons. So the modern interpretation of a tachyonic field is instability, not FTL. There are no real particles in such a field that travel faster than light. The math looks like FTL at first glance, but the actual physics is about the field being in an unstable configuration and wanting to roll to a more stable one. Real tachyons, particles that actually move faster than light, have never been observed. There is no experimental evidence for them. The most famous apparent observation was the Opera experiment in 2011, which measured neutrinos travelling from CERN to the Gran Sasso laboratory in Italy, and found they arrived 60 nanoseconds faster than light would take. The physics world held its breath. 60 nanoseconds. If real, it would be the most important experimental result in a century. It wasn't real. Subsequent investigation revealed two instrumental errors: a loose fibre optic cable connecting the GPS receiver to the detector electronics, and an oscillator running slightly too fast. When both errors were corrected, the neutrinos arrived exactly when they should, at, not above, the speed of light. Tachyons, in the particle physics sense, remain purely theoretical. We've mentioned exotic matter, matter with negative energy density, several times now in the context of wormholes and warp drives. Let's dig into what physicists actually mean by this and why it's so problematic. In classical physics, energy density is always positive. Mass is positive. The gravitational field of any mass attracts, always. Negative mass, negative energy density, would gravitate repulsively. It would push away from ordinary matter rather than attracting it. In quantum physics, as we mentioned with the Casimir effect, you can get regions of negative energy density. regions where the local energy is less than the vacuum. This is real. It's been measured. But it comes with restrictions. The quantum inequalities, formalized by Ford and Roman in the 1990s and 2000s, place constraints on how much negative energy can exist in a region of spacetime, for how long, and over what volume. You can't just manufacture arbitrary amounts of negative energy. Producing a region of large negative energy density requires enormous positive energy density nearby, concentrated over very short timescales. The net effect of all the quantum inequalities is that the amount of negative energy density producible by any physical mechanism in any region of space over any reasonable timescale falls catastrophically short of what would be needed for macroscopic wormholes or warp drives. Just how short? The estimates depend on the specific configuration, but for a traversable wormhole of, say, 1 meter diameter, small enough for nothing useful to fit through, the required exotic matter has negative energy of approximately -10 to the power of 32 joules. That's roughly the total energy output of the Sun over its entire 10 billion year lifetime, in negative energy, concentrated in a ring around a 1 meter hole. For a warp bubble large enough to contain a spacecraft, the numbers are worse. Even Harold, White's optimized geometry requires negative energy that, while reduced from Alcubierre's original estimates, is still many orders of magnitude beyond anything we could conceivably produce. The energy condition. Question. The reason exotic matter is forbidden in classical general relativity comes down to something called energy conditions, mathematical constraints on the stress-energy tensor, the mathematical object that encodes matter and energy content in Einstein's equations, that most physically reasonable matter satisfies. The weak energy condition says, for any observer, the local energy density of matter is non-negative. No observer should see negative energy density. The null energy condition says, for any light-like direction, the corresponding component of the stress-energy tensor is non-negative. This is weaker than the weak energy condition, but still rules out exotic matter. The strong energy condition and dominant energy condition impose additional constraints. Classical physics satisfies all of these. Quantum physics violates the weak and null energy conditions, but only in small, transient, constrained ways, like the Casimir effect. Wormholes and Alcubierre warp drives require violations of the null energy condition. Specifically, they require regions of negative energy density that persist in time and extend over macroscopic volumes. Current quantum physics doesn't appear to allow this at the required scale. Whether future physics, a completed theory of quantum gravity, or some new understanding of matter and energy, might allow macroscopic exotic matter is genuinely unknown. We can't rule it out. We can't rule anything out that our current theories don't address, and quantum gravity is very much unfinished business. We've touched on this theme throughout the video, the connection between faster-than-light travel and time travel. Now it's time to confront it directly, because it's not just a curiosity or a footnote. It's possibly the deepest reason why FTL might be fundamentally impossible, even in a universe where exotic matter exists. The argument goes like this. In special relativity, any method of transmitting information or matter faster than light can be used, by combining it with ordinary relative motion between reference frames to transmit information or matter backward in time. This isn't a bug in a particular FTL scheme, it's a feature of the mathematics, a direct consequence of the Lorentz transformation, which is the bedrock of special relativity. Let's work through this carefully because it's worth really understanding. The loop has no consistent resolution. It's not just weird or counterintuitive. It's logically contradictory in the same way that this statement is false is logically contradictory. There's no fact of the matter. This is why physicists treat the possibility of backward time travel with extreme seriousness. Not because they're worried about killing their grandfathers, but because a physical theory that allows backward causation seems to allow logical contradictions, and a universe with logical contradictions in it doesn't make sense. There are a number of proposals for how physics might resolve, or prevent, causal paradoxes from FTL or time travel. Igor Novikov proposed that only self-consistent histories are possible. If you go back in time and try to kill your grandfather, you will fail. Not because time travel is impossible, but because in a consistent universe, you didn't succeed. That's part of the history of the universe, and you can't change it. In this view, closed time-like curves are possible, but only events that are self-consistent can actually occur. You can travel back in time, but whatever you do, there was already part of history. You cannot create a paradox because paradoxes are not self-consistent, and only self-consistent histories exist. This is elegant but deeply unsatisfying. It implies that your actions in the past were somehow determined before you made them, that there's no free will in a time travel scenario, because only one consistent outcome is permitted. It also raises the question of how the universe selects which consistent history occurs when multiple are possible. The many worlds interpretation of quantum mechanics, and its time travel extension, suggests that instead of a single timeline, every quantum event branches the universe into multiple histories, one for each possible outcome. Time travel, in this view, sends you to a different branch, a different parallel universe. You don't change your own past, you create a new branch where the past is different. This resolves the grandfather paradox. You can kill your grandfather in the new branch, because that branch is not your origin branch. Your origin grandfather, in your origin branch, is still alive and still fathered your parent. This is satisfying in a certain way. But it requires accepting the many worlds interpretation, which is not universally endorsed and has its own deep philosophical problems. It also means time travel isn't really travel to the past of your universe, it's travel to a different universe that resembles your past. As we discussed in the wormhole section, Hawking proposed that quantum effects would always prevent the formation of closed time-like curves, time machines, through a feedback process. Any attempt to build a time machine would unleash runaway radiation that destroys the device before it can be used. If Hawking's conjecture is correct, and it might be, we don't know, then any FTL travel that would create a time machine is automatically blocked by physics. The universe enforces causality actively through quantum field dynamics, rather than passively through mathematical prohibition. This would mean wormholes, if they form at all, always snap shut before they can be used as time machines. Warp drives, if they could be built, would be spontaneously destroyed when their configuration would allow causal loops. Physics would be self-censoring, always finding a way to prevent violations of causality. In the philosophy of physics, the block universe view, also called eternalism, treats all moments of time as equally real. Past, present, and future all exist, equally, in the four-dimensional space-time manifold. There is no privileged now. The universe is, as a whole, a four-dimensional block, and our experience of moving through time is an emergent, perhaps illusory property of our position in the block. In an eternalist universe, you can't actually change the past because the past is fixed. It exists, fully formed, as part of the block. Time travel in this view is just motion along the time axis of the block. What you do in the past was always what you did. It's part of the fixed block. There's no paradox because there's no changing of anything. The history was always what it was, including whatever you did when you travelled to it. This is consistent with a deterministic view of physics, and it's philosophically coherent. But it's metaphysically troubling to many people, because it seems to eliminate free will entirely. If the block is fixed, everything that will ever happen has already happened in some sense. The real question. The deep question that these scenarios expose is this: does the universe have a logical consistency requirement baked into its physics? And if so, what mechanism enforces it? In our current theories, causality is enforced by the speed of light. No signal, no influence, no causal relationship can propagate faster than c. This is the cosmic firewall against closed causal loops. If you remove it, even partially, even in principle, you need something else to enforce consistency. Chronology protection, self-consistency, many worlds. These are all proposals for what that something might be. We don't know which, if any, of these applies to the real universe. We don't know whether the universe has a mechanism for preventing causal paradoxes beyond the light speed limit, and without a complete theory of quantum gravity, we may not find out anytime soon. Here's something that might surprise you. There are things in the universe that move faster than light. Not hypothetically, not in principle, actually right now in the universe we live in, and none of them violate special relativity. This seems paradoxical until you understand what special relativity is actually prohibiting. The limit isn't on how fast things can appear to move, or how fast certain patterns or structures can spread, or how fast space itself can expand. The limit is on the transmission of information, causally connected signals, through space-time. The distinction matters, and understanding it reveals a lot about the structure of the universe. The most dramatic example is the expansion of the universe itself. We live in an expanding universe. Every galaxy is, on average, moving away from every other galaxy. The further apart two galaxies are, the faster they're receding from each other. This is Hubble's law, discovered in 1929. At a distance of about 14.5 billion light-years from us, a sphere called the Hubble radius, galaxies are receding at exactly the speed of light. Beyond the Hubble radius, galaxies are receding faster than light, not moving through space faster than light. The space between us and them is expanding faster than light can cross it. The light emitted by a galaxy beyond the Hubble radius is moving toward us at c, but the space it's trying to cross is expanding faster than it can travel. The light is losing ground. It will never reach us. This doesn't violate special relativity because special relativity applies locally. At any given point, local physics obeys the speed limit. The FTL recession is a global geometric effect. Space growing faster than light can traverse it. The observable universe, the sphere of space from which light has had time to reach us since the Big Bang, is smaller than the total universe. The total universe may be much larger, even infinite. We are seeing only the part close enough that its light has had 13.8 billion years to reach us. Light travelling through a medium, glass, water, air, slows down. The refractive index of the medium reduces the speed at which the light wave's wavefronts propagate. In water, light moves at about 75% of c, in glass, about 67%. But this is the phase velocity, the speed at which the peaks and troughs of the wave propagate. The phase velocity, in certain exotic circumstances, can exceed c, in what's called anomalous dispersion, which occurs near the resonant frequencies of certain materials. The phase velocity of light exceeds c. This has been measured in laboratory settings. Pulses of light have been measured propagating through certain media at multiple times. c. Does this transmit information faster than light? No, because the phase velocity is not the velocity at which information is transmitted. The information in a light pulse is carried by the group velocity, the speed at which the pulse's envelope, its overall shape, propagates. In anomalous dispersion conditions where phase velocity exceeds c, the group velocity remains below c. More precisely, a light pulse doesn't contain a single frequency. It's a superposition of many frequencies. Each frequency travels at a slightly different phase velocity. The group velocity, the speed of the pulse as a whole, is determined by how these frequencies interfere. In normal dispersion, group velocity is less than phase velocity. In anomalous dispersion, this relationship can be reversed, but information, being encoded in the modulations of the pulse, its changes, always travels at or below c. This is one of my favourite examples, and it's simple enough to picture immediately. Imagine an enormous pair of scissors. The blades are light years long. You begin to close the scissors. The point where the two blades intersect, the cutting point, moves along the blades. If you close the scissors fast enough, the intersection point can move faster than light. Not just slightly faster, arbitrarily faster. If the scissors are long enough and you close them fast enough, the intersection point races down the blades at any speed you choose. Does this violate special relativity? No, because the intersection point isn't a thing. It's a geometric feature, a position where two extended objects happen to meet. No material is moving faster than light. The blades themselves are moving slowly. The apparent motion of the intersection point is just a mathematical consequence of the geometry. You can't send a signal using the intersection point because you can't use it to carry information from one place to another. The point appearing at position x at time t doesn't cause anything to happen at x. It's just a description of where the blades happen to cross. In astronomy, there are real, observed phenomena that appear, at first glance, to violate the speed of light. Active galactic nuclei, the energetic cores of galaxies with supermassive black holes, often produce jets of plasma that shoot out from the black hole at near light speed. When astronomers measure the apparent transverse velocity of these jets across our line of sight, they sometimes measure velocities of 5, 10, even 20 times c. This is not a violation of special relativity. It's a projection effect. If a jet is moving at 99% of c, but it's aimed nearly toward Earth, at a small angle relative to our line of sight, then it's chasing its own light. The jet was there at time t1, emitting light. At time t2, it's somewhere else emitting light. But the light from t2 was emitted from much closer to us than the light from t1, because the jet was chasing us. So the t2 light arrives very shortly after the t1 light, even though 2 minus t1 was a long time. The jet appears to move much further in a short time, apparent superluminal motion. But the jet itself was never moving faster than c. Apparent superluminal motion in astrophysical jets has been an understood effect since the 1960s, and is completely consistent with special relativity. Here's a more subtle example that generated genuine controversy in the 1990s. Quantum tunneling is a quantum mechanical phenomenon where a particle passes through a barrier that, classically, it shouldn't be able to penetrate. An electron approaching an energy barrier higher than its kinetic energy would, in classical physics, simply bounce back. In quantum mechanics, the electron has some probability of appearing on the other side of the barrier, as if it tunneled through. What's the transit time through the barrier? How long does tunneling take? This question is surprisingly tricky. In 1993, physicist Gunter Nimtz measured microwave photons tunneling through an undersized waveguide, effectively a classically forbidden barrier, and found that the photons appeared to traverse the barrier in 0 time, or slightly less than the time it would take light to travel the same distance through free space. He played a segment of Mozart's 40th Symphony using the tunneled signal and claimed it had been transmitted faster than light. This result was real, the measurement was accurate, but the interpretation is disputed. The issue is what exactly is travelling through the barrier. In quantum tunneling, the particle's wave function has an imaginary wave number inside the barrier. It doesn't oscillate, it decays exponentially. The peak of the wave function appears to travel through faster than c, but it's the phase velocity that's doing so, not anything that carries information. When you try to transmit information, actual data, not just to carry a wave, you need to modulate the signal. Modulations in the signal cannot propagate faster than c through the barrier, even when the carrier appears to. The group velocity of the information-carrying modulations respects the speed limit. Most physicists accept this interpretation, that quantum tunneling does not actually transmit information faster than light. But the debate has continued at a more technical level, because the exact definition of tunneling time is genuinely subtle and not fully resolved. If you shine a powerful laser at the moon and sweep it across the lunar surface, the spot of light on the moon can travel faster than c with no difficulty. The moon is 384,000 kilometers away. A laser sweep that takes 1 millisecond from left to right would move the spot across the moon at about 1.3 million kilometers per millisecond, more than 4 times the speed of light. But again, no information travels faster than light. The spot is not a thing, it's a pattern, a correlation between the position of the laser on Earth and the position of the illuminated point on the moon. Each photon still travels from Earth to the moon at c. The spot appears to move fast because the photons arrive at a series of points in rapid succession, but each photon is independent. You cannot use the laser spot to signal someone on the moon faster than light. The person at the right side of the sweep would see the spot arrive at them when photons from the right side of your sweep reach them, a bit over a second after you pointed the laser at them. They don't receive any information from the left side of the sweep that travels faster than the photons from that side. All of these examples, phase velocity, scissors, superluminal jets, quantum tunneling, laser spots, share a common feature. What appears to be faster than light is not a causal influence. It's not carrying information. It's a pattern, a geometric feature, an apparent motion, a correlation, but not a signal, not a causal connection. And that's the key distinction. Special relativity doesn't prohibit patterns from appearing to move faster than light. It prohibits the transmission of causal influence of information faster than light. These two things look similar but are deeply different, and the universe has been remarkably careful to allow the former while preventing the latter. This is where I want to push back against two narratives that are both wrong. The first narrative is the enthusiast narrative. Scientists are close to developing warp drives. The technology is just around the corner. We're on the verge of a breakthrough. This narrative appears in breathless press releases, science news aggregators, and social media accounts. It's almost always overblown. The second narrative is the dismissal narrative. Warp drives are pure science fiction. No serious scientist works on this. It's a waste of time. This narrative appears in the comments sections under every article about FTL physics, often from people who haven't kept up with the field. It's also wrong. The truth is more interesting than either. There is real, legitimate peer-reviewed physics being done on FTL-related topics, published in reputable journals, by physicists at accredited institutions. The work is serious. The results are genuine. But the gap between interesting theoretical physics and working technology is enormous, and honesty requires acknowledging that gap clearly. So let's talk about what's actually happening. The Limitless Space Institute, LSI, in Houston, Texas, is one of the few organizations dedicated specifically to studying the physics of advanced propulsion, including warp drive concepts. Founded in 2019 by former NASA engineer Harold White and former astronaut Franklin Chang Diaz, it operates as a non-profit research institute. Harold White, whom we met earlier in the Alcubierre warp drive section, has continued working on warp drive geometry at LSI. His group has been exploring specific configurations of the warp field that minimize exotic matter requirements while maximizing transit capabilities. In 2020, the German startup Applied Physics published a paper, co-authored by White and his LSI colleagues, proposing a new class of positive energy warp drive that, in their analysis, doesn't require exotic matter. This paper got enormous press. The headlines were predictably breathless. Scientists design working warp drive. This was an overstatement. What the paper actually showed was a specific space-time metric that the authors claimed represented a self-consistent solution to Einstein's equations for a warp drive-like geometry without requiring exotic matter. The subsequent peer review was skeptical. A number of physicists pointed out issues with the analysis. Questions about whether the geometry was truly free of exotic matter requirements, whether the proposed configuration was stable, and whether it actually achieved superluminal travel or merely described a moving mass. The community has not converged on the paper as a genuine breakthrough. But the work is ongoing, the questions are real, and LSI continues to publish. In 2026, White's group published a paper on a modified warp field geometry they call the nacelle configuration, drawing on certain aspects of the familiar Star Trek design language, but grounded in actual differential geometry. The paper explores whether distributing the exotic matter, if achievable, in a different spatial arrangement reduces the instabilities of previous designs. This work is at an early stage, and the exotic matter problem remains unsolved, but it represents genuine theoretical progress. The 2021 paper by Alexei Bobrik and Gianni Martir that we mentioned in the Alcubierre section has had continuing influence on the field. By providing a general mathematical framework for all possible warp drive geometries, rather than just Alcubierre's specific solution, they've allowed researchers to explore the full space of possibilities more systematically. Following their paper, several groups have explored specific corners of this space. What geometries come closest to the energy requirements that future technology might conceivably achieve? Are there configurations that are more stable, more controllable, or easier to engineer than Alcubierre's original? This is legitimate theoretical physics, happening now in 2026. The honest conclusion from this body of work is that subluminal warp drives, warp fields that move at below C but might offer propulsive advantages over conventional systems, are the more near-term target. True superluminal warp drives remain firmly in the realm of theoretical exploration. The conjecture that Einstein-Rosen bridges and Einstein-Podolsky-Rosen entanglement are the same thing, ER equals EPR, has generated substantial research activity since Maldacena and Suskind's 2013 paper. The key question the research program is trying to answer: what is the precise mathematical relationship between the entanglement structure of a quantum system and the geometry of the spacetime it defines? If this relationship can be made mathematically precise, it would give us a handle on quantum gravity, the currently missing theory that combines quantum mechanics with general relativity. This matters for FTL travel, because wormholes and their traversability are, in this framework, ultimately questions about quantum information theory. Whether you can traverse a wormhole becomes a question about whether you can perform certain quantum operations on highly entangled systems, and that potentially is an engineering question about quantum computers and quantum information not just a question about exotic matter. This doesn't mean quantum computers are going to open wormholes anytime soon, but it does mean that progress in quantum information theory might illuminate the physics of wormholes in ways that purely classical general relativity cannot. This is one of the most exciting research frontiers in fundamental physics. The most fundamental obstacle to confident answers about FTL travel is that we don't have a complete theory of quantum gravity. General relativity is our best theory of gravity and space-time geometry. Quantum mechanics, specifically quantum field theory, is our best theory of matter and energy. Both are extraordinarily successful in their respective domains. Both make predictions that match experiments to extraordinary precision, but they're incompatible at a fundamental level. General relativity is classical. It describes continuous fields and smooth geometries. Quantum mechanics is fundamentally probabilistic and discrete. When you try to apply quantum mechanics to the gravitational field, to quantize gravity, you run into mathematical infinities that quantum field theory can't handle the way it handles the other forces. String theory and loop quantum gravity are the two leading contenders for a theory of quantum gravity. Both are fascinating. Neither is experimentally confirmed. Neither is complete. And the questions that matter most for FTL, what happens to space-time geometry at the Planck scale, whether Hawking's chronology protection conjecture holds, what the quantum nature of wormholes is, require a complete theory of quantum gravity to answer with confidence. Until that theory exists, we are working with an incomplete set of tools. Our answers about what is and isn't possible may be wrong in important ways. This is not a counsel of despair. The history of physics is full of examples where the mathematics pointed to possibilities that seemed ridiculous. Antimatter, black holes, gravitational waves, and turned out to be real. It's equally full of examples where apparently reasonable ideas turned out to be impossible. We're in genuinely uncertain territory, and genuine uncertainty in physics is exciting. Here's an indirect line of evidence that's worth considering. The Fermi paradox. The question of why, given the billions of planets in our galaxy and the billions of years the universe has been around, we see no evidence of intelligent life beyond Earth, has been extensively analysed. One resolution to the paradox is that FTL travel genuinely is impossible. If interstellar travel requires thousands or millions of years, even at near-light speed, the galaxy is effectively isolated into independent civilizations that never meet. The absence of alien visitors isn't mysterious, it's expected. The universe is big, travel is slow, and nobody bothers because it takes too long. Another resolution is that FTL travel is possible but extraordinarily difficult, perhaps requiring a level of technological development that most civilizations never achieve. Or perhaps the energy required, even with optimized warp drives, is so vast that only the most advanced civilizations ever manage it. Neither of these resolves the Fermi paradox definitively, but the FTL question and the Fermi paradox are deeply linked. If it turns out that FTL is genuinely impossible, the Fermi paradox becomes much less mysterious. And if FTL turns out to be possible, the Fermi paradox becomes much more pressing. Why aren't they here? Let's be concrete about the propulsion technologies that exist in the realm of plausible with extensions of current physics. Nuclear pulse propulsion, like the abandoned Project Orion, could achieve perhaps 5 to 10% of the speed of light with existing physics. No exotic matter required. A fission or fusion bomb-powered spacecraft could get to Proxima Centauri in perhaps 100 years. Slow, but not hopeless for robotic probes. Laser sail propulsion, the concept behind Breakthrough Starshot, uses a laser array on Earth to push a lightweight sail, achieving possibly 20% of C. The Breakthrough Starshot initiative is an actual funded project with actual engineers working on it. It could send a gram-scale probe to Alpha Centauri in about 20 years. Getting data back would take 4.2 years more. Fusion propulsion, specifically if we crack controlled nuclear fusion, could achieve exhaust velocities significantly higher than chemical rockets, potentially enabling 10 to 15% of sea speeds for crewed vessels. Not FTL, but dramatically better than anything we currently have. Antimatter propulsion is the most energy-dense option within conventional physics. Matter-antimatter annihilation releases 100% of the mass as energy, compared to nuclear fusion's 0.7%. An antimatter rocket could theoretically reach significant fractions of C, with the light cone and time dilation effects we described earlier. The problem Producing antimatter at scale is currently absurdly inefficient. We can make nanograms per year at particle accelerators at enormous energy cost. None of these is FTL. All of them are interesting. All of them are more realistic near-term targets than warp drives. The FTL question remains open. The near-term question, how do we travel interstellar distances in any reasonable time, has answers that don't require exotic physics. They require enormous engineering effort, but they don't require negative energy density. Let's pull back to the very large picture. We began this video standing outside at night, looking at a star that's probably dead, its ancient light still travelling toward us across centuries of void. And we've travelled through some of the strangest, most beautiful, most demanding physics humanity has ever developed. We know what light is: an electromagnetic wave, a quantum of the electromagnetic field, massless, always travelling at c, experiencing no time at all. We know why c is a limit, not because we've chosen it as a rule, but because it's the conversion factor between the space and time dimensions of a four-dimensional universe, woven into the structure of reality at the most fundamental level. We know what special relativity actually says, that time is not universal, that simultaneity is not absolute, that moving clocks run slow, and moving rods contract, and the energy cost of going faster diverges as you approach the speed limit. We know what it would actually feel like to approach c, the aberration of the star field, the blue-shifted radiation bath, the interstellar medium becoming a particle beam. We know about wormholes, Einstein and Rosen's bridge, Morris and Thorne's traversable version, the exotic matter problem, the stability problem, Hawking's chronology protection, the ER equals EPR conjecture. We know about the Alcubierre warp drive, real mathematics, exact solution to Einstein's equations, fantastical engineering. We know about quantum entanglement, real non-locality, definitively proven by Bell's theorem, useless for FTL communication because of the no communication theorem. We know about tachyons, imaginary mass, causality destroying antitelephones, tachyonic fields in quantum field theory meaning instability rather than FTL. We know about the things that genuinely do move faster than light, expanding space, phase velocity, laser spots, astrophysical jets, and why none of them transmit information. We know about the grandfather paradox, chronology protection, the block universe, the self-consistency principle, and we know where the field stands today. Serious physicists doing real work on warp drive geometry, on the ER equals EPR connection, on the quantum gravity theory that might eventually answer the deepest questions. We know the honest gap between the mathematics and the engineering. We know what's possible in principle and what remains far beyond our current grasp. So where does this leave us? Let me be honest with you, because this subject deserves honesty more than it deserves hype. Faster than light travel in the conventional sense, a spacecraft moving through space-time at v greater than c, is ruled out by special relativity with about as much confidence as any result in physics. This is not a rule that future technology will circumvent. It's a mathematical consequence of the structure of space-time, confirmed by every precision experiment ever performed. It is not going to change. Wormhole travel and warp drive travel, the geometrical approaches that circumvent c rather than exceeding it locally, are not ruled out by known physics. They're ruled out by engineering reality, which is a different thing. The known physics actually permits them, in principle. The engineering requirements are so far beyond our current capability, and so dependent on physics we don't yet understand, quantum gravity, exotic matter production, that we cannot even confidently project a time frame. It's not like fusion energy, where we've demonstrated the reaction, and the challenge is engineering. It's not like room temperature superconductivity, where we know what we want and are searching for the right materials. It's more like saying we want to build a perpetual motion machine. Except crucially, the underlying physics doesn't say it's impossible. It says it's possible in principle, but requires something, exotic matter, that we can't produce with known physics. The honest answer to will we ever have FTL travel is, we don't know. And that's not a dodge. It's the true state of our knowledge. What we know for certain is that our current physics is incomplete. General relativity and quantum mechanics are the two best theories in the history of science. They make predictions accurate to astounding precision. GR predicts the precession of Mercury's orbit, the deflection of light by gravity, the rate of energy loss from binary pulsars, and the existence of gravitational waves, all confirmed. Quantum field theory predicts the magnetic moment of the electron to 12 significant figures, in agreement with measurement to 12 significant figures. These are triumphs without parallel, but they're incompatible. They cannot both be exactly right. At the Planck scale, 10 to the power of minus 35 meters, 10 to the power of minus 43 seconds. The smooth space-time of GR and the probabilistic quantum fields of QM are in fundamental tension. We need a theory of quantum gravity to resolve this tension, and the questions that matter most for FTL, the nature of space-time at Planck scales, the fundamental status of exotic matter, whether chronology protection is a rigorous theorem or a conjecture, these are questions that quantum gravity will address. We may find that wormholes are completely forbidden at the quantum gravity level. We may find that quantum gravity provides new mechanisms for space-time engineering that classical GR doesn't know about. We genuinely don't know. And this is the most exciting statement in physics. We genuinely don't know. Before we close, I want to invoke history. The history of physics is littered with things that were obviously impossible and turned out to be real. Atoms were considered philosophical speculation for millennia. They were obviously unobservable and therefore meaningless. Boltzmann drove himself to depression and eventually suicide fighting for the atomic hypothesis against the consensus of his day. He was right. Curved space-time, the idea that gravity is not a force but a geometry, that massive objects bend the fabric of reality itself, was incomprehensible to many of Einstein's contemporaries. The mathematics was obscure, the concepts were alien. We now use it to navigate with GPS satellites. Black holes, singularities in spacetime where gravity becomes so strong that even light cannot escape, were considered by many, including Eddington, one of the most respected astrophysicists of his era, to be mathematical artifacts without physical meaning. They are observed in every major galaxy in the universe. Quantum entanglement, the instantaneous correlation of distant particles, was described by Einstein as spooky action at a distance and dismissed as evidence of an incomplete theory. It's the basis of quantum computing and quantum cryptography. It's real, it's non-local, and it works exactly as the incomplete theory says. I'm not saying this history proves that FTL travel is possible. It doesn't. History also contains plenty of examples of things that turned out to be genuinely impossible. Perpetual motion, squaring the circle, the ether. But history does prove this. Humility is warranted. Our current understanding is incomplete. Our current tools are limited. And the universe has repeatedly surprised us with possibilities we didn't anticipate. The dream of faster-than-light travel isn't fundamentally about speed. It isn't about the romance of spaceships or the aesthetics of science fiction. It's about a much deeper human need. We are, as far as we know, alone on this planet, and possibly in this galaxy, and possibly in the observable universe. We have sent probes to the edge of the solar system. We have landed on the moon. We have orbited Earth thousands of times and looked back at our pale blue dot. And we have seen, more clearly with every passing decade of astronomical observation, that the universe is unimaginably vast, and that it is, apparently, full of everything needed for life, planets, water, organic chemistry, billions of years. And yet we are here, alone, unable to go and look, unable to reach out, unable to know. The scale of the loneliness implied by our current physics is difficult to fully absorb. If FTL is truly impossible, then humanity, or whatever we become, is forever isolated in this corner of the Milky Way. We can explore the solar system. Perhaps we can reach nearby stars over centuries or millennia of travel. But the vast majority of the universe, the billions of galaxies, the trillions of stars, the potential civilizations and wonders we can barely imagine, is permanently beyond reach. This is not a small thing. This is an existential constraint on the scope of everything human civilization might ever be or do. And that's why the physicists who work on warp drives and wormholes aren't crazy. They're not deluded. They're not wishful thinkers ignoring the math. They are staring at the mathematics and finding the cracks, the places where the mathematics itself seems to allow, in principle, a way out. And they are pushing on those cracks with everything they have, because the alternative, giving up and accepting that we are forever local, forever bounded, forever island dwellers in a boundless ocean, is not something human curiosity allows. There is a profound philosophical truth that emerges from all of this. The speed of light is not just a physical constant. It's a mirror held up to our civilization, asking, what are you, and what do you aspire to be? Everything we've discussed, the relativistic effects, the wormhole solutions, the warp drive mathematics, requires not just new technology but new physics, new understanding. It requires pushing the frontiers of human knowledge into domains we haven't mapped yet. It requires solving quantum gravity. It requires understanding the quantum nature of space-time. It requires, perhaps, discovering entirely new physics that we haven't yet guessed at. In other words, it requires us to become much wiser than we are. And maybe that's the point. Maybe the speed of a light isn't a cage. Maybe it's a challenge, a bar set at exactly the height needed to force our civilization to grow up, to stop fighting over oil and borders and to start thinking on timescales and spatial scales appropriate to the universe we actually inhabit. Carl Sagan, whose novel Contact inspired Kip Thorne to work out the physics of traversable wormholes, said something that has stayed with me. The universe is not required to be in perfect harmony with human ambition. He's right. The universe owes us nothing. It didn't arrange itself for our convenience. The speed of light is what it is, not because it was designed to limit us, but because it's what the geometry of space-time requires. But Sagan also said this: somewhere, something incredible is waiting to be known. That too is true. The history of physics is the history of humanity stumbling upon incredible things it didn't know were there. The atoms, the quantum, the curvature of space-time, the Big Bang, dark matter, dark energy, that mysterious pressure, 68% of the universe's energy budget, that's accelerating the expansion of space and that we understand almost nothing about. The universe is full of incredible things waiting to be known, and some of them, we don't yet know which ones, might change everything we think we know about what's possible. We are an extraordinarily young species doing extraordinarily early physics. Homo sapiens have existed for about 300,000 years. Modern science, the experimental, mathematical, empirically accountable science that produced special relativity and quantum mechanics, has existed for perhaps 400 years. General relativity is 110 years old. Quantum field theory is about 90 years old. If our civilization lasts another million years, if we don't destroy ourselves or collapse, if we keep pushing, keep learning, keep building on the foundations we've laid, how much physics will we know then? We cannot answer this. We cannot even meaningfully guess. The physics of a civilization 1 million years ahead of ours is as incomprehensible to us as quantum field theory would be to a Neanderthal. The concepts don't exist yet. The language to describe them doesn't exist. The mathematics doesn't exist. And yet that civilization, if it exists, will look back at us, at this video, at these words, at the Einstein field equations and the Alcubierre metric and the no communication theorem, and they will see the early, fumbling attempts of a young species to understand its universe. They will see the questions we asked and marvel that we managed to ask them as well as we did, given how little we knew. And they will know whether FTL is possible. They will know what quantum gravity says. They will know whether the universe allows a way out of the light-speed cage. We just have to last long enough to find out. Here is what we know for certain. The universe is vast beyond comprehension. Light, the fastest thing in it, takes 100,000 years to cross our galaxy alone. The physics we have tells us that moving faster than light through space is impossible for anything with mass. The same physics, paradoxically, contains mathematical structures, wormholes, warp drives, that might allow circumventing this limit without local violation. These structures require exotic matter and engineering capabilities so far beyond current technology that they might as well be magic. The questions they raise about causality are deep and unresolved. The theory we'd need to answer them, quantum gravity, is unfinished. What we do not know, whether quantum gravity will open new possibilities or close old ones, whether exotic matter can be produced at macroscopic scales, whether Hawking's chronology protection conjecture is a theorem or a conjecture, whether the ER equals EPR conjecture will lead to new physics, whether there is physics beyond the standard model and general relativity that changes the picture entirely. The speed of light is the most important number in the universe, not because it limits us, though it does, but because it's the key that opens the deepest questions physics has ever asked. Is the universe a closed room, or does it have a door? We don't know yet, but we're working on it, and until we find out, until some physicist, in some year we cannot predict, working with tools we cannot imagine, unlocks the answer. The correct response is not despair, and it's not false hope. It's something much more exciting. It's curiosity, because in physics, curiosity is never wasted, and the universe, for all its indifference to human ambition, has never once failed to reward those who look at it hard enough. Thanks for watching, Cosmic Pup family. This was a big one. If you made it to the end, drop something in the comments. I want to hear what blew your mind most. Was it the time dilation math, the Alcubierre metric, the causality arguments, the ER equals EPR conjecture? Like and subscribe if you want more deep dives like this. We're just getting started. Bye bye guys.